On a surgical robotic project which is a collaborative project between UNCW and Johns Hopkins University. Okay, so whenever you're ready, go ahead.
So my name is Charlie Caputo, and this is a semi-autonomous control interfaces for surgical robots, mentored by Dr. Saidi. We're going to go through the context of the project overview, the proposed solution. I'll show you a functional product, and then the next steps pretty much after I'm gone. So robotic-assisted surgery has been around for a couple decades now, and it has revolutionized modern medicine by introducing things such as tremor filtering and motion smoothing, which increases reliability and efficiency. With robotic-assisted surgery, we introduce a topic called levels of autonomy. At level 0, it is full surgeon control. The robot is not doing any filtering or any tasks. At level 1, we introduce these filtering methods to help steady the hand of the surgeon and increase reliability and efficiency. At level 2, we start to introduce small tasks, allowing the robot to autonomously do small tasks, but the surgeon is there the whole time to take control at any point if needed. At level 3, we give more control to the robot, but the surgeon's still there overviewing all the tasks that the robot does. At level 4, the robot is pretty much doing the whole surgery itself, but the surgeon is there to take over at any point and is there to approve and set up the procedure. At level 5, there is no human in the loop. It is purely autonomous mode. Currently, existing solutions contain things in the realm of bone surgery, which is, we have the Mako robot that you see here. It is currently at a level 1 with new level 2 versions of it coming out. For soft tissue surgery, you have things like the Da Vinci surgical system. Does things such as anastomosis, or it's used for procedures such as anastomosis and tumor resection. And this is also level 1 with level 2 emerging. In the field of radiology, you have things like the CyberKnife. This is an outlier as it is a level 4 autonomy. The surgeon essentially sets it up, and because it's radiology, it's not physical tools going into someone, it's beaming radiation at targeted tumor cells. And it's a great breakthrough in technology. But today, we're going to be focusing on soft tissue surgery. So in soft tissue surgery, you have 3 subtasks. The first is incisions, where you can have the surgeon doing cutting tasks, things for like tumor resection, where you're cutting a tumor out. Here you'll see level 2 autonomy, where we're in autonomous mode, and then we switch to manual, surgeon's in control, and then we switch back to autonomous, robot's back in control. This video was taken from Dr. Saidi's lab. This is a work that I worked on a little bit, but mostly came before me. Another thing, the next task is suturing. This is stitching, known as stitching. You'll see this is level 2 here, where this robot comes down. It's going to try and suture. It does miss, but then it corrects itself as it realizes it misses. This was also taken from Dr. Saidi. This was some of his work at Johns Hopkins. And then the third task, and I'm going to give anyone who is squeamish a warning. You're going to see
I'm
some
already
intestines
squeamish.
here.
I don't know what that is.
Yeah, this one's worse. The third is grasping. So this here, you'll see the grasping is usually a supportive item in which you're actually manipulating tissue in an area so that you can do what you need to do, cut, suture, whatever. I won't leave that up for too long, but yeah, so you have those 3. Right now, that last video that you saw was a level 1 autonomy. There was a surgeon in there with just some small filters. Between all 3 of these projects, you have a very similar control block diagram where you have a table that you're working on, you have a way to see it, usually a camera, you have some form of markers and a path pointer so that you can use the path pointer to tell the robot where you want it to go. Then you make a trajectory pointer that takes the path and tells the robot like how to actually execute that path. And then the robot feeds back into that trajectory pointer. So today we're going to be focusing for this Capstone project on reaching level 2 autonomy with grasping. So like I said, we're going to try to make an autonomous controller for grasping tasks, and we're going to make a semi-autonomous control interface for the grasping tasks. That'll help us achieve a level 2 autonomy. This is a part of a more bigger project where we're trying to, again, achieve level 2 autonomy for robotic-assisted surgery, where we can have robots working in tandem to complete these tasks, preferably 3 robots, one doing cutting, one doing suturing and one that can grasp and manipulate. Before I get into the nitty-gritty of the Capstone project, I want to talk about the path planner that we're going to be using. I want to just talk about how it works a little bit and validate it a little bit, because this is very important when testing autonomous controllers, because any errors in the path planner will cause errors in autonomous control, especially in like precision and accuracy. So, a collaborative path planning strategy for robotic soft tissue surgery. This was a project that I worked on in Dr. Saeedi's lab. We just recently published with JMRR. Essentially, the surgeon can select key points, and between those key points, our path planning algorithm will set a bunch of waypoints so that the robot can follow those waypoints. Surgeon has to select less points. Spacing errors and other things go down so that you don't have as much mistakes. The surgeon doesn't have to spend as much time doing this portion. The path planning algorithm uses a low-cost function. That's how it's able to avoid things like these obstacles. And yeah, with pilot tests, we had a small problem in which we're using this haptic device. This haptic device can move around in a 3D environment, the pointer can. And so when you're working on a surface, you're working on almost a plane. It may have curves, bumps, whatever in it, but it's pretty planar. When you add something that's 3D and try to convert it to 2D, you can get a lot of noise if you're away from your reference area. And so to mitigate that, we add two things. First is a force feedback system, which you'll see in this video. Essentially, the haptic device will push and pull me and try and keep me on that surface. That way I can mitigate error. And then the next thing is a visual cue. You can see when I pull away from the surface, you can see my dot gets bigger, my pointer gets bigger, and you can see some of that jitter there. And then when I go in, it'll start to become a little bit transparent. You'll be able to see it, but it looks like it's disappearing and going away from you. And then here you can see this system kind of working all together. So there's me with the headset on. This is what I see right here. This is what the computer sees. And I'm using the haptic device to place all those points. After pilot and preliminary tests, we did a final test. We had 8 participants, total of 8 conditions per participant. And it was a mix of assisted, which is having that path planner enabled, versus unassisted, where the surgeon has to select every single point. Then you have the force feedback, no force feedback, visual cue, and no visual cue for the tests. And then for A, that is the training scenario. For B, that is test condition 1 and 2, where the user will start either top or bottom, do a circle. Or at the second condition, they'll do left or right and do a full circle. For C, they'll start either left or right and do a figure 8. And for D, they'll start top or bottom and do a figure 8. Overall, we got some great metrics from this. There was a decrease in things like spacing error, probability of corrections, and completion time. Just kind of showing how this system makes it easier for surgeons to select points when trying to do this path planning. So now that we have the path planner covered, let's get into the nitty-gritty of the project. So the proposed solution, we're using a lot of the same stuff from the previous projects, especially the incision project. We have the head-mounted display, HMD, which you see here. It's a Quest 3. We have the haptic device. The haptic device is used to select points and control the robot, and in this case, control the grasper. You also have a set of pedals that allows you to confirm the plan, switch modes at any point, and start and stop the robot. Then we have the RealSense D415 camera, which is this guy here. It's a depth camera. That's what gets us our point cloud. That video that you saw before with a bunch of dots in it, that's what allows the robot to see what's going on. Then you have the 2 stereo cameras, which allows the surgeon to see what's going on. You'll see image from both of these in the head-mounted display. And then we have the UR5E, the robot that we're going to be using. And lastly, we have the Da Vinci Crocodile Grasper tool, which is mounted using an adapter designed by researchers at Southern Denmark University. We went with this because this is actually what Da Vinci uses, and they're a very established company in the medical robotics world. So for this project, we have a few requirements. Obviously, level 2 autonomy, we need to be able to switch from manual to autonomous mode at any point, specifically from autonomous to manual. Then we also need to be able to actuate the grasper in both of those modes. Then we have trajectory execution. We need to make sure that the robot can do a task on its own after getting a plan. And then workspace modeling, we need to have a simulator to model and practice and make sure, like validate the system that we're using to ensure that we don't have any problems when we don't destroy a $30,000 robot. Then we have a ROS modular architecture. This is very important because, again, we're trying to bring together multiple robots. Having a modular architecture, especially in ROS, allows us to use a lot of resources all together very easily. And then lastly, we have performance thresholds. So in the literature, active retraction or grasping tasks, they are allowed to have a 2mm error. Anything under that is considered successful, anything above that is considered bad. So my goal was to try and get an average that was 25% below that 2mm error. There's no reason I wanted to get under like that specific 25%. It was just a personal goal that I had. But being able to get under that 2mm error was a big goal for this project, at least for the validation part of this. So we started off with a prototype. Like I said, we have a simulator. Specifically, this one was borrowed from the Incision project, where I just manipulated it and changed it so that we changed the kinematic chain to add this new adapter, new tool. You can kind of see it working here. You can see me and Manuel trying to get this thing to move around. And you'll see here that it's doing the legacy cutting task. The reason I wanted to leave this in here and not show a new video is because I wanted to show that this trajectory planner, we're taking this trajectory planner and we have to change it. And the way we're doing that is instead of following each of these points, we start to extrapolate points. You can see that here. So 2 cyan points, those are the user selected points. The red points are the extrapolated points from those 2 user selected points. We have a starting position up here, a grasping position here, and a retraction position. This is for the tongue retraction test. The reason we do this test is to validate that we can actually grab tissue-like items and manipulate them properly. And here you can kind of see a video of this working. You can see my 2 selected points all the way over here. And then you see it comes down, grab, and retract. For the second test, this test was made to be a precision and accuracy test. So what we did was we tried to pick up a thumbtack and move it and put it back in to this piece of foam. And then we just hand drew some marks on this version. For the actual tests, which you'll actually see in the video that I play, we printed out a grid so that we can get uniform spacing and everything. But here we also are extrapolating a bunch of points. We're extrapolating 3 more points here, or 3 more. We have 2 points that are selected by the user. We have a starting position, a grabbing position, retraction, then we move to this position, we place the thumbtack in, and we retract again. And you can see that here in this video. Bless you. So from these tests, we got all right results. Again, this is just a pilot test for future work, a small stepping stone to validate that the system that we have set up in this capstone actually does work. And the results are as follows. We measured the mean positional error. For the autonomous mode, we got 1.51 millimeters plus or minus 0.58 millimeters. So you can see my average is 0.01 off from my goal. For me, the human, I had a 1.5 millimeter error with a variance of 0.98, and the p-value is 0.963, which means that these aren't significantly different, which is good in this case because it means that we're not adding any new problems. It's very similar. They both have a similar average, and they work well. They're both within that error, that allowable error. And then for the task time, the autonomous mode did a little bit better than me. I'm also no surgeon, so take that with a grain of salt. It did the task in 34 seconds. That is from it starting to move to it stopping the movement. So going down, grabbing, moving, placing, and retracting. Same for me. I took around 37 seconds. So for future work, we are going to design an algorithm to track the tissue in the tool. This will hopefully get rid of a lot of the errors that we have, A, positional error, and B, any mechanical error from the tool. Because the tool's really long and we have problems with the tool bending, it's very flexible. And then to validate this future system, I went ahead and built a gimbal to mimic movement and show that we can actually track what's going on. And you can see kind of that here. This was our prototype. It's much smaller. I built a bigger one here. But we're using leftover motors from the Grasper because we originally bought 4 in case we needed all 4 to actuate the tool, but we went with a simpler tool for this. But you can see me here manually manipulating the Grasper tool, trying to get this string, and you'll see I'll kind of pull it side to side. Now the reason they would do this, and this is a copy of like anastomosis. The reason they would do this is so that they can get a suture into the middle here more easily, and by manipulating the skin and giving themselves like more area to work in. Because you can see kind of how we have this like curve here. It can be difficult to kind of get in and do that suture without hitting the back wall. But if we can manipulate the skin, make this wall a little bit straighter, then it's easier to work on. Here are my references. And I want to thank Dr. Saidi for bringing me onto this project. I want to thank A.C. Kraus, A. Mezip Pantoja, A.C. Lawson, and Axel Krieger. Also, Dr. Cohen for laying the foundation for this project. I wouldn't have been able to do it without any of them. So, thank you.
So when did you sleep at a Holiday Inn? You're a surgeon now. Yeah.
I don't think so. I don't know if you saw that video. I'm very shaky. I could never be a surgeon. I need the tremor filter.
I got it. What are some of the biggest things that you take away from this as you think about your future?
I've always kind of, well, not always. In high school, I kind of never knew what I wanted to do. I started doing engineering, and I didn't know what I wanted to do with engineering after that. Then I got here, and I was able to get on Dr. Saidi's project, and all I knew from then on was that I wanted to use this to help people, use my engineering skills to help people. I really like working in the medical world. I think it's a lot of fun. I think it's very interesting, and it's extremely difficult. There's like no tolerance for problems in your system. So it has a lot of constraints, it's difficult, and I love that challenge.
Thank you.
Speaking of tolerance, why is the tolerance a half a millimeter? Because it seems to me that it ought to be able to be lower than that, but of course this is not my area, so maybe that's normal, but it just seems that tolerance, and I get the human being has greater tolerance, but I'm surprised that you aren't able to get the tolerance below a half a millimeter.
So for this, we're not using any visual tracking, so a lot of the problem comes from mechanical errors. Let me show you. So the tool itself kind of looks like this. It's a box with a long pole. This pole can rotate around the z-axis. So if you're looking at the bottom of it, you have the pole right here. It can rotate around like that, right? So with that, you have a problem called runout. This happens in a lot of mechanical systems, where ideally, if you try and spin it, the point will stay in the same spot, but the head will just rotate, right? The problem is that doesn't actually happen. Usually what happens is it'll rotate in like a circle, like this. And so when I designed the system, I designed it so that with the runout in mind, the middle point will be there. So the actual runout is around 2 millimeters. So 3 millimeters actually. So that's why we're seeing kind of that 1.5 millimeter error, is because the runout of the tool, and trying to keep in mind that there is runout and setting the system up around that. Because if we rotate the tool and it's like, we have the system set up so that when it's at a 90-degree position, it's perfect. But then at a 270-degree position, it's 4 millimeters, 3 to 4 millimeters off. You know what I'm saying?
Mm-hmm.
So a lot of that comes from mechanical errors. And that's why we want to introduce things like an algorithm to actually track the tooltip. That way we can correct it dynamically during the surgery. So,
Yeah, I mean, that seems to me to be a big problem.
yes. And it's something
If
that...
your goal is to be within 2 millimeters, that's a big issue. So, I mean, either that needs a better designed device, which is beyond the scope of your work, obviously, or there needs to be something else by which you can compensate for it. So
That's why we're trying to do in the future work. The next person to hop on this will be working on that and getting that error to 0, as close to 0 as possible. Any other questions?
So you mentioned how, like with the DaVinci, you had to add that entire contraption on the end of the URE5 robot.
Yeah.
And so you guys actually added like the length of that joint into your kinematic equations?
Yes. So I was able to model it in the simulator because we had the CAD drawing for this portion of it, and then I had to add this end. But yes, it's reflected as a 7th joint in the kinematic chain.
Gotcha.
That way the robot can know where the actual tooltip is.
Gotcha. So you guys kind of had to go into the kinematic chain, break it out a little bit, and add that additional degree of freedom.
Yes.
That's really cool.
Just like that there. But great work. That's a photo of kind of the whole system together. But yeah.
And did you design all of those 3D printing housings, or is
No.
that what you got from the DaVinci team?
That's what we got from the researchers at Southern Denmark University.
Okay, gotcha.
So this, actually, let me go back to this slide. So from here to here is what they designed. I added one small part, which was to help stabilize it, because originally the runout was 5 millimeters. It was bigger, so I added a small stabilization thing to help kind of mitigate that. But yeah, that was the only thing that I designed for that.
Gotcha. Great work.
Thank you.
I'm always curious about the haptic device.
Yeah.
Because I did some of your pilot tests, I think, in the lab.
Yeah.
And then also Dr. Said brought that to class. We got to play with that like spherical, like the simulated orb.
Yeah.
I thought that was so cool. Because like you can really trick yourself into thinking that's there.
I know, and it's very like the motors on it are very stiff. So
Yes.
it feels like you're hitting a hard
Yes.
object if you really max it out.
And doing your tests,
Mm.
I really liked the force feedback. I like all of the tests without it felt like stupid compared to the force feedback. But you're saying that you have to do that because you're translating the 3-dimensional surface to a 2-dimensional.
Yeah, it's close
So-
to 2-dimensional. So you see,
Yeah.
like here, you can even see it like on
Right.
this tongue. There's like small bumps and stuff.
Yeah.
And I mean, obviously, you're trying not to go through an item,
Right.
right? Especially when path planning. So you're working directly on a surface, even if the surface is curved like my hand or there's bumps and ridges and whatnot. You are kind of working on a plane.
Right. My question is like why? Because actually trying the sphere,
Mm.
like that was super, like accurate and in real life, like felt real. So like why don't you use like a 3-dimensional surface and like try to get that same like force feedback? So it's like almost like, so if you like closed your eyes, it like actually felt like a real surface.
So
Or
a
does
lot
because the
of
force feedback didn't feel like it like completely
Yeah.
like captured that.
So when talking to surgeons, they actually hate, like, a lot of them dislike the force feedback and like tactile feel from haptic devices. They don't like the feeling of the tissue and stuff because they feel like it throws them off, especially for experienced surgeons,
Yeah.
because they're so used to knowing what it feels like. So when they feel something that's trying to mimic it, they don't. And this, obviously, we're not cutting, we're not doing the sutures in this specific like path planning stuff. So that force feedback isn't necessary for like tactile feel. You just place points.
Right, that's true.
So
Okay, so I guess you wouldn't even need that to be kind of overkill.
yeah, it
At
would
least
kind of
for
be
this,
overkill.
At least for this, yeah. Interesting.
Yes.
So in your study where you had real people using that, your N was 8. Why 8?
So we did a Latin square. So we had, which means that we had a certain amount of test conditions, right? We had 8 tests total that we're going to do with all of our stuff mixed. From there, we do a Latin square, which essentially is the optimized way to test all of those conditions with no bias from like the order of the positions. So 8 was the minimum number that we could do. We could have done more, but because we did 8 participants, 8 tests each, plus each one did a training and 4 tests, that was what, 256 conditions or something? It's a lot. It's a lot of conditions to do. It's and not a ton of time to do it. So we did what we could. So we picked
Hey,
it.
I understand that, just that that is one bit of criticism you might get,
Yeah.
is that your sample size is small.
Yeah.
That's,
That is a criticism we did get, I believe, for when we tried to submit it before.
Yeah.
But
yeah, and I understand, it takes time.
yeah, thanks a lot. Any other questions?
Real or gummy tongue? Which
Uh,
one would you use? I know that one's real.
Yeah, that
but
one's real. For the other one,
it's
it's like a fake tongue. It's a silicone tongue.
Okay.
Yeah.
So, yeah, sorry.
So when the robot is actually like suturing or cutting, if it moves the surface at all, does that change the path planning? Would that like cause error in the system as well?
So that's the idea behind the tracking. If we can track the tissue and how it moves, the point on it will be relative to the actual movement, so we can adjust the robot as it goes. Yeah. And that's also another thing with like the 2mm tolerance. There's, with the holding of items, there is a good bit of tolerance that you can have because it's a little more robust, certain things in the body. Usually what you're grabbing is like some connection between like a muscle and something else, right? So